Hello everyone. So from this lecture we are starting the analysis of statically determinate structures. So at first we will deal with the planar trusses. So in this particular lecture we are going to discuss how the planar trusses, statically determinate trusses can be analyzed, and this is somewhat points that we'll be dealing with in this particular lecture. So this is a chapter outline. At first we will discuss what are the assumptions that are being made while analyzing trusses, then sign conventions that are used, then we will discuss the different methods that are in practice for analysis of trusses, out of which just two methods will be dealing in detail, and we will solve some examples from method of joint and some examples from section method of analysis of trusses. So starting the chapter, what are the assumptions that are being made? I think we have discussed in very first lecture of structural analysis that what the truss members are, which kind of forces they do carry. Still, for the sake of revision, I will repeat it once again. Take an example of truss, a simple determinate truss. See, here it will have two reactions, here it will have one support reaction, and in total equations of equilibrium available are three equations, three unknowns. So static degree of indeterminacy is 0. It is a statically determinate structure. So whenever we are applying any load on, as because the joints are pin jointed, joints are hinged, in other words we can say, only axial forces can develop in these members. So these members are basically designed for axial forces only. So this is the very first assumption, only axial forces. So what is second assumption? The forces that we are applying on these structures, that means forces we are applying on trusses, planar trusses, are essentially applied on joints and nowhere else apart from joint. There cannot be a load like this. This is not allowed in trusses, except purlins. Purlins are the only member in trusses which may carry some bending stresses because of lateral loading, but nowhere else other than purlins. And most probably we are not going to discuss how to analyze the purlins in this particular chapter. So we can assume that loads are applied only at the joints. Then the third assumption is whatever joints we do have in these type of structures that are hinged joints, and that should be frictionless joint. If at all there is some friction, then we cannot, until and unless we do not know the parameters of that friction, like coefficient of friction and all, so we cannot do the ultimate analysis. We cannot implement our equations of equilibrium. There will be number of unknowns increased, and so the problem will become complicated. So for the sake of simplicity, we are considering these joints as frictionless joints. Then again, one more assumption we are making, that all these members, they have some self-weight, but while doing analysis we will neglect the self-weight. Self-weights are negligible as compared with the loads, axial loads that they will be carrying. So negligible self-weight. Again, one more assumption is made, which is also important, that all the truss members that are straight and not curved ones, once they become curved, there will be additional stresses induced, and we don't want them to do so. So all the truss members will be straight and they will carry axial forces only. So these are some assumptions that you must keep in mind. Straight members. So these are basic 5 assumptions that we have made while doing analysis of plane trusses. Okay, now we will move on to the second point in this lecture, that is sign conventions. So what system we will follow to decide what is the nature of force that a member is carrying. See, particularly in truss structures, consider a joint A, consider joint C. It has 2 members. If I draw a free body diagram of joint C, it has 2 members, member CA and member CB. So there will be an internal force like this, F. I will denote F for force and the member that carries that force as a subscript. So this is free body diagram of joint C. It has 2 members meeting at that particular joint. So that joint will be exerted 2 forces, one by this member and another by this. So actually in analysis of trusses, we decide the nature of force in perspective of this joint. So nature of forces are joint perspectives. If the joint is getting stretched because of the force, then we will say that the force is tensile. So in this particular case, this joint is getting stretched or force is pointing away from the joint. So as it is pointing away from the joint, or it is stretching the joint, in other words, we will say that the force is tensile. And in other case, consider joint A. If the force is like this, pointing towards, so this was force in member CA, we will call this force in member AB. Here there is end B, so force in member AB, which is pointing towards the joint, and so that makes it to be a compressive force. So this is in particular the sign convention that we will be using throughout the analysis of statically determinate trusses. If the force is acting towards a joint, then we will say that the force is compressive. If the force is acting away from the joint, then we will say that the force is tensile, or the member that carries the force is in tension. So for ready reference, I will just point here. Suppose this is a joint and force is towards the joint, which implies it is negative or compressive. A force acting away from joint, which implies it is positive or tensile. Okay, moving on to third point. What are the different methods that we normally use while analyzing trusses? So in practice there are 4 methods as such. The very first is method of joint. Second one is method of section. Then comes the graphical method. And ultimately there is one more method which is called as tension coefficient method. In method of joints, normally we find out the forces, we work out the forces, internal forces in members by considering equilibrium of each and every joint. So that is why it is called as method of joints. In method of sections, we normally take section at some particular points of a truss, and then we will implement the equations of equilibrium, global equilibrium of course. This was local equilibrium of joints. In this we will consider global equilibrium of the cutout section, and then we will work out the forces, internal forces. In graphical method, normally it is we normally draw the forces where they are meeting, and by graphical solution we can find out what the internal forces are. In tension coefficient method, we use a term called as tension coefficient, which has dimensions of Newton per meter, and that tension coefficient for each member remains same, and that helps in finding out all the internal forces. So for syllabus, I think these two methods are not there. We will mostly be dealing with first two methods. You might have studied these methods in your applied mechanics, but just we will have a quick review of both these methods, and we will learn how to speed up your process of solving the truss problem by either by method of joint or method of section. Of course, you know these methods, but we will just be dealing with how to speeding up the path. So here comes the method of section. Each and every method has its advantages and disadvantages. So this method of joints is one of the simplest methods, and it has some plus points. The very first is it is useful when a number of forces at a joint or number of unknown forces at a joint are just 2. So I'll just write down the plus points. If number of unknowns are equal to 2, then it is most useful method. Secondly, it is used in simple trusses which have a fewer number of nodes or fewer number of joints. In trusses which have few joints only. So this is very useful method if these two conditions are there in the problem, and it has some demerits. Of course, when the number of unknown forces get exceeded by 2, if data unknowns are more than 2, then it becomes a complicated method. The efforts required are much more. Secondly, it is very laborious method if you are supposed to find out internal force in such a member which is located away from the joint, because in this method we will be basically starting from joints and we will move forward. So if the joint that connects the member in which we are interested in, so that joint, if it is located away from the support reaction, then basically the time required will be more, and it will take number of joints to be solved in between, and it will also consume lot of our time. So it is laborious. Okay, now we will discuss which are the actual steps or what is the algorithm of this method of joints. What steps are involved if we are intended to solve a problem by using method of joints? The very first is working out reactions, support reactions. Before any truss to be solved, we must work out the support reactions. What are the magnitudes and natures of support reactions? That must be known before beginning the problem. Secondly, select any joint which has two unknowns only. Two unknowns means select such a joint which has only two members connecting to it, and start from that joint, analyze that joint first, consider the equation of equilibrium, all the equations of equilibrium. Of course, when we are talking about a local equilibrium of a joint, then I specifically mean that summation h and summation v only, because summation m we cannot apply on a joint. It has to be applied for a plane at any point in a plane it can be applied. So that means it is the same anywhere, so it's not independent anymore, but the equations summation h and summation v are separate for each joints, and we can apply them for local equilibrium of that particular joint. So consider equations of equilibrium for that joint which we have considered first. That will give you the forces, internal forces in members connecting that particular joint, and then move forward. Once you know the forces, then that members will be connected to some other joints, and consider that joint and repeat the procedure once again and keep going. Ultimately you will land up with the internal forces in all the members. Once that are known, your truss is analyzed. As simple as that. For example, I have a truss here. It has two panels. Hinge support at one end and roller support at other end. It is subjected to a load W here and another load, horizontal loads, both of them here. One more vertical load is here at a midpoint. So number of members are exactly equal to 2j minus 3, so there is no internal indeterminacy. Support reactions: hinge 2 support reactions, roller 1 support reaction, in total 3. Number of equations of equilibrium available are also 3. So we have 0 external indeterminacy. Both of the indeterminacies are 0, so statical indeterminacy is 0 and the structure is statically determinate, and hence we can apply any of the methods that I discussed just now. We will go with method of joint first. Yeah, of course I forgot to mention length of each panel, length and height of each panel is L. So how do we do? Basic step is to solve the structure for reactions. Reactions must be known. How do we find out the reactions? Just name all the joints: A, B, C, D, E and F. Consider joint A first. what we know is that summation of moments at any point in a plane is equal to 0. So we can apply that equation for global equilibrium. When we are talking about reactions, just consider that I am talking for global equilibrium only. So we can have this equation implemented here. Summation of moments at A is equal to 0. So what that will give us, just consider which forces are passing through joint A. Number 1, okay, is this passing through this joint? No way. This? No way, it has some perpendicular distance. Is this passing? No way, this will have some vertical reaction like this. This is also not passing through this point, so this will give us a 0 reaction. The moment of this force will be 0. Then what will be moment of this force? W will be equal to W into L. WL, and it is in clockwise direction. Same is the case with this vertical load W. Moment due to that load will also be equal to W into L, and it is in clockwise direction. Perhaps initially what we have assumed is this load will be vertically upwards. It's our assumption that this load is vertically upwards. So from our assumption, the moment that it will generate about this point will be in anti-clockwise direction. So I do here, sorry, here both were clockwise, so I just wrote here plus, and according to our assumption, the load at the support reaction at E, vertical reaction at E, will generate anti-clockwise moment, hence it comes negative. And what will be the moment? Suppose this is VE, vertical support reaction at E, and its moment is equal to 2L, L plus L, 2L. So this all must be equal to 0. Work out this equation and you will find that VE is equal to W, and as V comes out to be positive, our assumption is right, so the load is acting vertically upward. Got it? We have worked out the reaction at E. Now consider the next equation of equilibrium that is available with us. Which is it? Say summation of horizontal reactions is equal to 0. How many horizontal reactions do we have? One horizontal reaction here. Oh, sorry. How many horizontal forces do we have? One here and one here. So we have a, I just forgot to mention, when we are talking in a global sense, we have some sign conventions. If it is horizontal load acting towards right, it will be positive. If it is vertical load and if it is acting upwards, vertically upwards, then it will be considered as a positive, and negative on these sides. Fine. Initially what we will consider is support reaction at A is acting towards right, horizontal reaction at A. So this HA is towards right, HA. Again this load is also acting towards right, so plus W, but this is acting towards left, hence minus W is equal to 0. Any other, of course, no load in horizontal direction. So from this, HA comes out to be equal to 0. Fine. loads are balanced, there is no horizontal reaction. Once you know horizontal reaction, similarly we can find the vertical reaction also. Summation V is equal to 0. This load is acting downwards, this reaction is vertically upwards. We know the magnitude also. Again, what do we know? We have to find out this reaction. We have considered initially it to be acting positive in upward direction. What do we have? One force, two force, and three forces in vertical direction. So just equate both of them, all of them. What we will get is, so this is VE positive because it is acting upward. Considered VA also positive, and minus W is equal to 0. So this will give us V at A is equal to 0, because this is also equal to W. Plus W minus W gets cancelled and we have VA is equal to 0. So now basically we have worked out all the reactions, I guess. Now we will move on towards finding the internal forces. This is 0, HI is of equal to 0. So our second step was start from such a joint which has minimum number of members associated with it, or in other words it has just two unknowns. So do we have such a joint? Yes, at B. Consider joint B first. Draw a free body diagram of joint B. It is subjected to load W. So what kind of force is expected from this member? What kind of force this member will exert on this particular joint B? Of course, if it has to be in equilibrium, it will exert a force in left direction, isn't it? This is W, and what kind of force will be there in this vertical member? As there is no any force acting, external force acting on this member which is in vertical direction, so this member will oppose no one. This has no one to oppose. It will basically a zero force member that will be, because it has no external force to equilibrate. So when we just have to consider summation H, sigma H equal to 0, which means force in this member. What is that member? BC, which means FBC, which is in this direction as per our assumption, and in this particular force, so minus FBC plus W is equal to 0, and FBC is equal to W. But remember, what kind of force is it? Compressive. So I will just mark the force and its direction here. It is W. And we are done with two members. Of course, this is a zero force member. Again, which joint do we have for consideration? You can have this joint. No, it has three unknowns associated. Can you consider this? Yes, of course, because now force in this member is known, which makes number of unknowns at this particular joint reduced to 2. So just start this one. consider joint A. In joint A, we have something like this, which is this is reaction VA. Then again a force W. Of course, this is also a zero force member. So I'll better rub all these portions which have zero force. So free body diagram of joint A stands like this. It has, so to oppose this force it will develop some force like this, and in order to equilibrate this force, this horizontal force, the horizontal component of force that this member will carry has to be in left direction, and for that the member must carry force like this, compressive force. So these are our basic assumptions. Now we will consider the equations of equilibrium. Summation of V equal to 0. If summation V is 0, what it makes? There is no vertical force other than a vertical component of this. So if there is just one force acting in any direction, then that means it is a zero force member. So vertical component will be 0 for this member. If vertical component is 0, that means member has zero force. Then if this has zero force, then all the force should have to be resisted by this member alone, and hence the force in member AF will be tensile in nature and of the magnitude of W, exactly equal to the force acting on joint A. So we are done with 1, 2, 3, 4 members. Now we can move on to joint number this, joint F. What is there in joint F? There is a load acting vertically downwards, and yeah, we know an internal force in member AF, FAF, which is equal to W. This is the simplest problem or the simplest joint when we consider as a equilibrium in horizontal direction. What we will get, this force is resisted alone by force in this member, because there is no any horizontal force or horizontal component. These are exactly vertical, they cannot have any horizontal components. So AF and AFE will be exactly equal and opposite in direction. So I have pointed the direction, and magnitude will be equal to W. Same is the case with vertical members. It will oppose vertical load alone, and it will develop a tensile force of magnitude W. Now we can handle this joint E. It has one vertical, one horizontal. Here the horizontal force is exerted by this member which is attached to it. There is no horizontal reaction as such, support reaction as such. With this, in order, we are done with joint F. See, there is a vertical reaction at joint E. internal force W. So in order this joint to be in equilibrium, this horizontal reaction has to be opposed by a horizontal component of this member, this inclined member. So it will have a force in this direction. Got it? If it has a force in this direction acting in this direction, it will have a horizontal component acting in the right direction that will oppose this internal force. Again, if it has a force acting in this direction, it will develop a vertical component which is in vertically downward direction. So for that force to oppose, this member must carry vertically upward force. Okay. So these are our initial assumptions, we can say. Now we will actually move on to work out all these values and the signs, whether they come out to be right as we assumed or not. Now we will consider horizontal equilibrium first. If summation H has to be equal to 0, W must be equal to a component of that, as this angle is 45 degree, as we know, LL. So both of the, it's a right angle, and all the angles other than that 90 degree are 45. So we have 45 degree angle. So horizontal component of this force, which is nomenclature is EC. EC's horizontal component is cos 45. FEC cos 45 degree. Okay. So if we solve this, we get FEC is equal to, because there is no any other horizontal force, FEC is equal to root 2W. So once we know value or magnitude of force that is carried by EC, we can easily calculate its vertical component. And when we consider summation V equal to 0, there are few more forces acting, which is vertical component of this, which is equal to W, or according to our assumption it is minus W. Vertically it will act downward. Then again there is this force, which is F, what we say ED, minus W. FED is acting upwards, and there is one more upward support reaction. These all have to be equal to 0. As these get balanced, FED is again a zero force member. Again we will simply consider joint D, that is the last joint remaining, and it has no vertical force, similarly no horizontal external force, hence this member will also be equal to, the force in that member will also be equal to 0. So now we are with us nature of all the forces with their magnitudes. If you want to have a check, the last joint that we haven't analyzed, we have analyzed all these joints A, B, D, E, F, except C. If you want to have a check on whatever you have done is right or not, you can just analyze joint C. You know all the forces because all the members are solved. Just apply the equations of equilibrium, summation H equal to 0, summation V equal to 0, and if you are getting it, means summation H is coming out to be equal to 0, and so is the summation H, then and only then whatever you have done is right, not otherwise. So this is one of the advantage that this method of joint has. It gives you a check. You can implement that check and you can verify whether your answer is right or not. So that was all about method of joints. Now we will move on to method of section. Previously I have discussed the positive points of method of joints and so the negative points. Method of section is normally preferred where you are supposed to find out the internal force in a particular member only. If you are not concerned about forces in rest of the members, you can go for method of section. It's a quick method and it will give you an answer within fraction of seconds. So basically this is applied for determinate trusses only, and yeah, it has a basic step that you must calculate support reactions first. However, there will come some cases where you don't need to calculate support reactions even. You have a sections like this and you are considering a part of section, because in this method what we do is we just break up the section, we just break up the structure, we cut it at a particular section and we just analyze a separated part of it. We are not concerned about the equilibrium of whole structure. We are just talking about a part of structure which is removed from original one. If that part does not include any support reaction, that means there is no need to solve for support reactions even. I'll explain this with examples. Actually, method of section do also have some subparts. I mean, how one can implement the method of section. It has some ways. The very first is summation of moments equal to 0. These methods, the subparts are based on equations of equilibrium that we will use in that particular method. Very first we can use summation of moment, then similarly summation of H or horizontal reactions can also be used. Summation of vertical forces reactions can also be used. So depending upon which equation to use, mind you one thing, in this method of section we do not use all the equations of equilibrium. We will use just one equation of equilibrium and that will decide which subpart of method we are dealing with. It also depends upon how the member is oriented, the location of member. If members are inclined, mostly we will go for summation of moments. If members are horizontal, then we will go for horizontal. If members are vertical, then we will go for this method, summation b equal to 0. Of course, these are the thumb rules. The actual condition of section or actual decision of section has to be taken only after looking at overall conditions of the structure, or that all are case specific, but we can follow these thumb rules with no any exception. I'll start with the very first sub part of method, that is how we can use summation of moments to find reaction or to find internal force in any member. I have a structure. Hinge support at one end, roller support at other end. Consider all these members to be straight. A, B, C, D. Both the panels have same length and height. Okay, and now the problem is we are told to find force in this particular member. FED, force in this inclined member, is to be found out. So what is FAD? This is our basic problem. And yeah, as we are supposed to find internal force in just one member, we will go with method of section. And yeah, by thumb rule it is inclined, so we will go for moment equilibrium method. Then how to take a section? Mind you, when we are taking section, the very first point is it must pass through the member, or it must cut the member in which we are interested. As we are interested in member DF or FD, so it is F. As we are interested in member FD, the section must pass through this member. Along with it, the second point to remember is at which point we are going to apply the moment equilibrium. At which point we will apply equation of equilibrium, summation m equal to 0. If I decide to apply it at this point, then which are the forces or which are the sections which can have moment about this point? Basically this is the one, and one more is this, isn't it? Let us say, I can have a number of sections as such. It is ultimately upon you to which section to decide. So I will just decide a vertical section which is oriented like this. It passes through member FD and member FE. Again, when I find out reactions, because as I am concerned with, I have decided to deal with the left part. So left part includes a support reaction, and when I am considering global equilibrium of this left part, support reaction has to be known. So I will just go for calculating support reactions first. If I work them out, the support reactions are coming to be W by 2 and W by 2. As the structure is symmetrical, both reactions are equal. There is no horizontal reaction at point A, as there is no horizontal external force. I know the reactions. I will just deal with this left part. I will draw a free body diagram of left part. Okay. And doing summation of forces at this joint. See, this vertical reaction is equal to W by 2, force is equal to W at this point, and I am concerned about force in this member, isn't it? Consider global equilibrium summation M at, which is this point, F equal to 0. What it means, this force, moment of this force will be equal to 0. Moment of this vertical reaction will be equal to W by 2 into L. It is in clockwise direction. I am taking it as positive. Summation. I'm extremely sorry. Actually, we are interested in finding out force at this member, CD member. And as I have decided to apply moment equilibrium at this particular point, that means this member and this member's moment will be equal to 0 because of this section I have chosen, So this has some force, so does this member, and also this member will have some force. Say it is FCD. Initially I have assumed it to be like this, in this nature, and when I calculate moment equilibrium, it is W by 2 into L for this support reaction, and moments of all these forces will be equal to 0. So plus 0, moment of this force now plus FCD into L. So this is must be equal to 0, which means FCD is coming out to be negative W by 2. What does this negative sign indicate? Negative means what we have assumed, the direction that we have assumed is wrong, and it is exactly opposite of that. So that means this will be of this nature, and which means FCD carries, or FCD is compressive in nature. It is acting like this, and its magnitude is W by 2. No need to solve other members for other members, no need to solve for other joints. So this was the first sub method, which is summation of moments. There are two more sub methods. Second is summation of H. If your structure is like this, of course it is a determinate structure, and it has some members, inclined members. You are interested in member AB. As member is horizontal, you will go for summation H equal to 0 as per thumb rule, and you can pass a section like this. While passing a section, the thing that you need to, of course I forgot to do a loading. It is subjected to load P here and the load PP here. So while passing this section, there is one thing to remember: it must pass through the member of interest. Secondly, when I am using this particular method, the section should be such that all the members that are cut by this section will not have any horizontal reaction as far as possible. So as these members were vertical, I just cut them. They are not supposed to have any, because they are not supposed to have any horizontal components. So I will consider the uppermost part, upper separated part. It does not include any support reaction. I need not go for them. Upper part is like this. This is P. I am interested in this force. I am assuming initially that it is in this direction. So FAB it is. Just apply summation H equal to 0. What it will give you? None of the separated members have. Wherever you cut the section, internal force will oppose it, as there is just vertical internal force in these members. So no need to count for it in horizontal reactions. Summation is equal to 0 means P is equal to FAB, or P minus FAB equal to 0, which makes FAB equal to P. Our assumption is also right, and we know the nature as well as magnitude for this magnitude of force for this member. It is P. Similarly, there is one more method, sub method. This was summation H equal to 0. Then how can we implement summation of vertical forces equilibrium equation, and how do we solve the problem? Suppose a structure is like this. It's a truss. Again, determinate, statically determinate, and you are supposed to find, loaded like this, force in member AB. It's a vertical force. Section must pass through the member of interest, so it will pass through this member. Again, as we have decided to implement summation V equal to 0, so the member should be cut in such a fashion that they will not develop any vertical reaction or vertical components. So which of these members will not have any vertical component? Of course, this is one, this is another. You can have a section like this. Separate out this part, have a free body diagram of it. It is P, joint B. We are not concerned about horizontal forces. Suppose FBA is in this direction. It's our assumption. When you implement summation V equal to 0, that will give you FBA is equal to P, or FBA minus P equal to 0, which means FBA equal to P. Now, you know the force magnitude and force nature in member AB. So this completes your method of section here. Now what we have remembered in this class, or what we have learned in this class, one thing, method of joints. We will use method of joints only when the structure is simple, and when it is required that we should know forces of all the members. Then it is one of the tedious one of the methods which require more efforts or which are laborious. Unlike method of section we use only when the member of interest are few, or just we are interested in finding internal forces in only one or two members. Then we will go for method of section. It has 3 parts, and as discussed, there are some thumb rules which will explain, which will guide you to use which sub method of section to use. So that is all about analysis of trusses. Thank you.